So now let's consider even more complicated situation, which is very difficult to solve using, for example, pairwise comparison, even with Bonferroni correction. It's when you have several factors, several potential factors. So this is my data set. You can see that in this case, I have still the chemical reaction, and then I have yield as a response. And then two factors. It's a temperature of the reaction, and you can see I have two levels, 120 and 160 degrees. And then the catalyst type, and catalyst type, I have three different catalyst types, right? So you can see I try all possible combinations. So I have 6 samples coming from 6 different populations, right? However, I have only 2 values, only 2 measurements, only 2 replicates within each sample. So my sample size is very small in this case, right? How ANOVA can help to handle this situation? Well, the idea is very similar. So first of all, we say, okay, if 2 factors do not interact, so they are independent. So if 2 factors do not interact, so they have its own effect without any interaction between these 2 effects, then this is the idea, right? So this is the values from the dark blue, and this is the values from the light blue cells of this table, right? So the idea is following, that these values, they came from population where the average yield is the sum of these 2, right? So it's an effect from having catalyst A and having temperature, the first level temperature, 120. And then in the dark blue, it's a sample taken from this population, the same average for the catalyst, but the average for the temperature will be different, right? So the idea is that these populations, they're different by means. Moreover, they're different only by mean effect from the temperature, right? Because effect from the catalyst will be the same because we don't change the catalyst. And why we do that? Because you remember that we have this assumption that all sigma are the same. So sigma of all 6 populations are the same, okay? Now we can simply extrapolate this to all 6 cases. So we have 6 cases, 6 different samples coming from 6 different populations. We know average. We don't know average, but we understand what kind of average we expect and what kind of standard deviation we expect from these populations, right? And that let us use the same idea like we did with ANOVA. We split or decompose all our values into sum of effects and random part, right? So in this case, the first term in the sum will be effect from the catalyst type. You remember we have 3 different catalyst type, and that's exactly this one, and this one, right? So in this case, we replace the values with average of the population, which we don't know. So this is just a theory, right? And then we can compute effect from the catalyst by calculating the variance of these average values. Likewise, we can add a systematic effect number 2, which comes from the temperature. So this is the temperature at 120 degrees. You remember that all these values, if you look at the original table, they came from the experiments where the temperature was 120 degrees. These are values that came from experiments with temperature 160 degrees. So these are values, actually. These are average values, right? So therefore, this is our expectations from the theoretical effect, number 2. And again, we can compute effect by computing variance of these average values, right? And then what is left, it's residuals. This is what we cannot explain with neither effect. So this is residual, this is random variation, and we know it should be normally distributed. And the standard deviation of this distribution, it's the standard deviation of the 6 populations that we have, right? So the same idea, the only difference is that we have now a second term in our sum, a second systematic term in our sum. We have sum of 2 effects plus residuals, right? Again, because we don't know the population, we substitute population with sample statistics. So instead of average of population, we have average of sample. So this is average yield of all measurements from here, right? So this is the average yield here. This is average yield here. This is average yield here. So this is the average yield within every catalyst. So within experiments where we use the same catalyst. Now, likewise, we have average yield for all experiments where we have temperature equal to 120 degrees. It will be these ones, and these ones, right? So we compute average of these 6 values. Then similarly, we compute average yield of all experiments where we had temperature 160 degrees. So it will be these, and these, right? And then finally, we compute residuals by simply subtracting. For example, we take x A11, it's this value. Then we subtract this. Then we subtract this. And that gives us the residuals A11, which we have here, right? So this is it. Now we know that we can compute variance. It's our observed effect for the catalyst type. Variance of these average values will be our observed effect for the temperature, and variance of the residuals will be the observed noise, right? I forgot to say that in this case we have two null hypotheses. Null hypothesis number one is that the catalyst doesn't have any effect. And then null hypothesis number two, it's that the temperature doesn't have any effect, right? So we have two null hypotheses, and therefore we have two independent systematic parts, systematic terms. So we need to compute F value for every hypothesis. So if we take this and this, we will have F value, the ratio of these two. We will have F value for the first hypothesis, and then if we take this and this, we will have F value for the second hypothesis, right? Let's do that. Well, first of all, these are my real values, and you remember it will help us a lot if we subtract the average, the grant average from the very beginning. It will make calculation of the variance easier, right? So that's what I'm going to do. This is grant average. It's average of all these values, and if I subtract it, I will get the distances, right? So these are distances. So this is minus 2.1 because this value is by 2.1 grams smaller than this value, right? And then I can compute the average A, average B, average C. All these average, if I compute average of these six values, it will be average for 120 degrees. This will be average for 160 degrees, which I also call like average 1 and average 2, right? So now we have everything to make this decomposition. So I say, now I use the biased version, so I don't use the original values. It's already the unbiased version, right, where I subtract the average. So we simply replace it with sum of three terms. So here we have systematic term. You can see that minus 1.1, 10.9, minus 9.9 here, right? This is the systematic effect from the temperature. Again, I use minus 2.1 here because I have minus 2.1 as average outcome when I use temperature 120, and 2.1 when I have 2.1 as the average for temperature 160. And the meaning of this is following. When I use temperature 120, by average, I have 2.1 grams less than the grant average, right? So the grant outcome, average outcome. And when I use 160, it's by 2.1 more. So in fact, I can see the effect, it's 4.2, right? So this is the difference here. So here I can compute the difference. But here I cannot compute the difference. I need to compute variance, and we simply compute variance for every case. So we just compute variance as our observed effect. So let's compute the variance, right? So we also have residuals. Let's check quickly. Minus 2.1, minus 1.1, it will be minus 1. Minus 1 minus 2.1 will be 1.1, and that's exactly what we have here, right? Let's do the other calculation. Sum of squared values. I simply square every value here and take a sum. That's the sum of squared values. Similarly, sum of squared values here, and then sum of squared residuals. Degrees of freedom, again, we had 12 values at the beginning. Then we subtract average, so 11 is left. Then we have 2 degrees of freedom for systematic part 1, 1 degree of freedom for systematic part 2, and then what is left, it's 8, right? So this is 2 degrees of freedom we use here because we have 2 independent distances. We have 1 independent distance here because you can see that they sum up to 0, right? So if I know that one value, one average for 160 degrees is 2.1, I know that the other one will be minus 2.1. So we have only 1 independent distance here. And then we have 8 here, which is 12 minus 1 minus 2 minus 1, right? Now we can compute the mean squares. It's simply a ratio of these two values. You can see a very large number. Ratio of these two values a little bit smaller. And then ratio of these two values, you can see very small numbers. So you can see that both variances are much larger than the random variance, right? Both systematic variance. We can compute the F-score. You can see 222 times larger. So no doubts in this case. 27 times larger. Again, no doubts in this case, right? So we have a pretty clear effect, pretty different from the noise. And we can compute the p-value. So again, you already know how to do it. You use CDF function for F distribution. This is the F value, degrees of freedom for systematic part, degrees of freedom for random part. So this is a p-value for the first null hypothesis, right? You remember this is the first null hypothesis. No effect from the catalyst type. And you can see we definitely need to reject it. And this is the p-value for the second hypothesis, no effect from the temperature. And apparently we need to reject this hypothesis as well. So it means that we have a clear effect from both factors. Again, as usual, I can do it in R as well. In this case, I just make the code shorter. So I took all these values as one long sequence. Then now I need to make two grouping factors, you remember. So here I have ABC, here I have 120, 160. You can check again, run this code in R and see what you will have inside G1, inside G2, and so on and so forth. And now look, this is the difference, right? So in this case, I say Y depends on sum of two effects, effect from G1 and effect from G2, and then I use sum, right? So that means that I expect that these effects are independent, that they do not influence each other, and therefore my result, my final result, it's a sum of two effects and also a random part, right? So the residuals. And then if we look at the summary, you can see that this is F value, this is what we got, this is the calculation, so it's almost the same. This is what we got, this is calculations, a bit different, but still a very tiny difference because you remember I round a lot of values when you do calculations. This is the p-values, and you can see that again they are similar to what we got here. Okay. So in this case, you can clearly see that we can expect that there is both effect from the catalyst type and effect from temperature. The only problem here is that we don't know how big this effect is. Well, we know the F value, that kind of a size of effect, but we don't know, for example, what happens if we switch to catalyst A from catalyst A to catalyst B. How much more yield we can expect in this case in average. Or what happens if we switched from temperature 120 to temperature 160. How much more yield we can get in this case, or less yield we can get in this case. All this information we still miss. We just know that there are two effects. There are effects from both factors, but we don't know how big the effects are. So it means that we still need to do the pairwise comparison, but we should do it in a smart way. So we should do it based on these ANOVA results, and that's exactly what I'm going to talk about in the next video.